Hello, we are Group 8 from FCMB. My name is Veer Dosi, and along with me are Rowan Jaiswal and Sparsh Jain. And today we will be presenting our mini project for SC1015. Our problem statement is that despite advancements in medical science, many individuals at risk of heart failure remain undiagnosed until the disease progresses to advanced stages. Traditional diagnostic methods can be invasive, expensive, and not universally accessible, creating a need for alternative early detection techniques. This issue hits close to home for me. A few years ago, a beloved family member passed away due to a misdiagnosed heart condition. It motivated me to leverage my skills in data science to develop a tool that could assist healthcare providers in making more accurate diagnosis of heart disease, potentially saving lives. Heart disease remains the leading cause of death globally, claiming millions of lives each year. Its symptoms can be non-specific and vary greatly, which unfortunately leads to frequent misdiagnosis. Misdiagnosing heart disease can delay critical treatment and ultimately increase the risk of fatal outcomes. Our dataset from Kaggle includes 918 entries across 12 clinical features. Our numerical data includes age, resting BP, cholesterol, fasting BS, max HR, old peak, and presence of heart disease, whereas our categorical data includes sex, chest pain type, resting ECG, exercise angina, and ST slope. Now let's discuss exploratory data analysis on our dataset. For the variable resting BP, while most subjects are within the normal range, the presence of subjects with higher values suggests a segment at risk. The correlation with heart disease is modest, indicating that it should be part of the risk assessment, albeit not the strongest predictor. The age distribution chart reveals a bell-shaped curve, suggesting a normally distributed age range, with most subjects falling between 50 and 60 years old. Older age groups seem to be more represented in the dataset, which aligns with the increased risk of heart disease in the aging population. The cholesterol graph exhibits a right screwed distribution, with a peak suggesting that most individuals have cholesterol levels around the 200 to 300 mg by dl range. High cholesterol is a significant concern for heart disease. Its negative correlation with max HR suggests that individuals with higher cholesterol might have reduced cardiac performance. Its negative correlation with heart disease in the heat map may need further investigation, as higher cholesterol is typically a risk factor for heart disease. In the fasting blood sugar chart, we see a bimodal distribution, where most individuals have a fasting blood sugar below the diabetes threshold, but a substantial number exceed it, highlighting a subgroup at elevated risk. Its positive correlation with heart disease reaffirms its inclusion in the predictive model. The max HR data portrays a near normal distribution with some outliers. A higher maximum heart rate during the exercise is generally healthier, as shown by the negative correlation with heart disease. Presence of heart disease outcome shows a nearly even split in the dataset, suggesting our dataset has a balanced representation of cases with and without heart disease, which is ideal for model training. The count of resting ECG results shows three categories. The normal category is the most frequent, followed by ST abnormalities, with LVH being the least common. These variations are essential predictors in our model. Exercise-induced angina is an important clinical marker. Our dataset shows a higher prevalence of subjects without exercise-induced angina, which can be a good prognostic sign. However, those who do experience it are at a higher risk of heart disease, making this variable a significant predictor. The correlation ship heat map provides a visual representation of how strongly each variable is related to another. We can observe that max HR is negatively correlated with heart disease, suggesting that higher maximum heart rates are associated with lower disease risk. Conversely, old peak shows a positive correlation with heart disease, indicating that higher ST depression is related to higher heart disease risk. Age also shows a positive correlation, which is consistent with the known increased risk of heart disease with advancing age. Our radar chart comes to life by plotting each health indicator on a separate axis, all originating from the same point. The function makeSpider creates one radar chart per group. This involves setting up the plot with polar coordinates and plotting the data points along each axis. We fill the area with features that will dominate the model due to its scale. We use standard scalar from the scikit-learn library for this purpose. With this visualization, we observe that individuals with heart disease tend to have higher cholesterol and resting blood pressure on average. In contrast, the maximum heart rate was typically lower in the same group. These findings reinforce the established medical understanding and offer a visual affirmation of the association between those metrics and heart disease. In conclusion, radar chart served as an innovative tool in our analysis. It's a compelling example of how creative data visualization techniques can sometimes lead to clearer insights. Next, we used a variety of machine learning models to find a suitable model for our predictive model. We first remove any rows with missing data to ensure our model only learns from complete records. Next, we tackled outliers, which can skew our model's understanding of trends. We identified outliers by examining the data's standard deviation and returned those that fell outside of an acceptable range. Many machine learning models require numerical input, so we converted categorical variables into a numerical format using one-hot encoding. This method creates binary columns for each category in a variable, which a model can interpret and learn from. We also scaled a continuous variable such as age, resting blood pressure, cholesterol levels, and maximum heart rate to have the same scale. This is crucial because it ensures that no single variable provides a good indicator of future importance, which is invaluable for interpreting the model. Random forest, which is a type of ensemble learning technique wherein it builds multiple decision trees and merges them to get a more accurate and stable prediction. It works well with a mixture of numerical and categorical features and prunes the curve to visualize the group's profile better. Gradient boosting is another ensemble technique that builds trees one at a time, where each new tree helps correct errors made by a previously trained tree. It's powerful for handling varied data types, and it's inherently a feature selection technique, often leading to more parsimonious models. Stacking, also known as stacked generalization, is an ensemble learning technique that combines multiple classification or regression models via a meta classifier in our case. The base level models are trained based on the complete training set, then the meta model is trained on the outputs of the base model. By integrating these techniques into one model, we have developed a system that not only accurate but also adaptive. It's designed to detect subtle patterns that may indicate the presence of heart disease, outperforming traditional single model approaches. Our approach harnesses these techniques together. Random forest provides a diverse set of classifiers, while gradient boosting offers refinements through focusing on mistakes. Stacking then takes these predictions as input, with logistic regression serving as the meta model to finalize the prediction. This creates a model that learns from itself, improving as it encounters new data. Now, we'll discuss the performance of various neural network classifiers. We experimented with different optimizers like ADAM, SGD, and RMS-prop to train our neural networks. Each optimizer updates the network's weight in different ways during training, impacting the model's learning efficiency and outcome. As you can see, the test accuracy and the test loss on both the trained data and the test data for each optimizer. Next, we provide the data-driven insights. Firstly, using the ADAM optimizer, we achieved a test accuracy of 88.04%. ADAM, which is known for its adaptive learning rate, which helps converge faster and more effectively. It's particularly effective in situations where the gradient scale is vastly different for different parameters. Next, the SGD optimizer provides a test accuracy of 86.41%. SGD, or stochastic gradient descent, updates parameters more frequently, which can lead to faster iterations. Lastly, RMS prop, which stands out for its ability to resolve the diminishing learning rates issue of SGD, led to a test accuracy of 88%. It adjusts the learning rate during training and is particularly effective for problems with noisy or sparse gradient. Now let's talk about the precision, recall, and F1 scores, wherein all models performed comparably. However, when it comes to ROC-AUC, a metric that is used for measuring the trade-off between true positive rate and false positive rate, RMS props slightly outperformed the others. Next, we'll show how we made some predictions. We processed the input data to match the pre-processing requirements for the model. Once the data is prepared with all the features, including newly calculated polynomial and interaction terms, it is fed into the pipeline. The model then predicts the presence of heart disease and calculates the probability of the prediction. For example, for the data user input 1, as shown here, the model could predict that it had no heart disease with a probability of 0.1214. Similarly, for the user input 2, the model could predict heart disease with a probability of 0.5513. After receiving the predictions, this application can also generate a PDF report, which includes graphical representations of risk over time as age increases and a pie chart showing the overall risk distribution. This report is designed to be used by healthcare providers for a better clinical understanding and further consultation. The overarching outcome is that while neural networks with advanced optimizers like RMS-prop offers high discrimination capabilities, the stacked model excels in overall accuracy and balance of metrics. It demonstrates the strength of ensemble techniques in making nuanced predictions, particularly in complex domains like medical diagnosis. Thanks a lot for listening to our presentation.